Okay, guys, I have some interesting news for you. And it's probably not as important for you all as it is for my 8 o'clock class, but just so you know, people who are late live longer. Heard it on the radio. Statistically, people who are late live longer. They have longer lives because we are optimistic, because we think we can get that extra thing done, so we do, and it makes us late. You will live longer. So see, I just want you to know that. So when you write that on my evaluation, she's late to class, just say, but she'll live longer because of it. So just remember that, okay? Or better yet, just don't write that. But if you do, just know I'm going to live longer because of it. I'm actually going to live till I'm 105. I've set that deadline for myself. Yeah. 105. If I live to be 105, then that means I will have seen, actually I'll have to live, let me think for just a minute, I have to do the math real quick. In 2076, yeah, that'll be okay. I don't even have to live quite to 105. I just have to live to July 4th of 2076 so that I will have seen the bicentennial and then the tricentennial. Okay? 2076. No, I wasn't, but I mean, I said almost 105.
Okay, sorry.
Almost 105. No. I just remember, when I was a little girl and I was almost 5. I was born in 71. Is my math right? Yeah, I was born in August of 71. I was born in August of 71. So I need to live to be 105 so I can see both the bicentennial and the tricentennial. That's my goal.
I just want to live long enough to get out of hygiene school.
To get off what? Hygiene school. Do you all know anybody who's over 100? How old is she? Just 100? That's awesome. That's awesome. Are you kidding me? Does she live alone? That's awesome. No way. Man, that's awesome. You got some good genes. That's good.
That's my goal right there.
That's awesome. All right, guys, we are going to finish up this test material. I've already sent you the email about the exam and the layout of the exam. That is all you will get regarding the exam, so we're not going to talk about that today. We're actually going to finish up this material, and so I should be talking about this instead of my life, but get out a calculator, and actually you won't need a periodic table. I don't think the other class used a periodic table. So get out a calculator and we'll fly through this material. Raj, are you here? There you are. Remind me to give you the sign-in sheet. All right, when we talked about acids previously, we said that an acid had what? Say it again. What did an acid have in it? It was in water, meaning dissolved in water, but so that's one of the things all acids had. They were in water, and they had what? Hydrogen. All acids had hydrogen. Our definition now is going to be similar to that, but there's a little bit of difference to that. But I'll tell you, if you went to a textbook and looked at what is an acid, honestly, you're going to find several different answers. You're going to find Bronsted Lowry definitions of acids. You're going to find Lewis definitions of acids, and there may be other definitions of acids. We are going to stick with the Bronsted Lowry definition of an acid and a base. So this is how we are going to determine if something's an acid or a base based on these definitions. It will still fit with what we said, so it's not against what we said. And that is that a Bronsted Lowry acid is a proton donor or hydrogen ion donor. What this means simply is that the acid that we're calling an acid has a hydrogen ion to donate. If it doesn't have a hydrogen, it can't be a Bronsted Lowry acid. It has a hydrogen ion to donate. Acids are opposite of bases in our world today. A Bronsted Lowry base is a proton acceptor or hydrogen ion acceptor. Again, what are we saying by this? We're saying it has the ability to gain a hydrogen ion or a proton. When we say proton, we mean hydrogen ion. Some common acids. These are some common acids that we know about. Obviously, if it says acid at the end of it, it's an acid. And acetic acid is an acid. It's got the formulas for you. Citric acid you've heard of. Does anybody remember the name of this one? Hydrochloric, hydrobromic, hydrofluoric. What's the next one there? You may know? Nitric. You don't say hydrogen when it's a polyatomic ion, so it's nitric acid. What's this one? Carbonate, so that became carbonic. Good, so carbonic acid, and you don't say hydrogen, just sulfuric acid. Do all those have hydrogens? So is that a hydrogen donor? And then it says other acids, coffee, lactic acid, apple juice, lemon juice, and milk is even slightly acidic. So when we say that they're acids, our world, this is where we struggle. These, chemistry-wise, we all see, yes, those are acids, we've named those, we know those. But then when I start talking about real world, it's like, well, what do you mean? I don't know the formula, and that's okay. Because another aspect of identifying acids or bases is looking at the pH, which we are going to do in a little bit. So we're actually looking at the world of, is it a hydrogen donor, is it a hydrogen acceptor, and what's the pH? We're not to the pH yet, but this is where we're looking at, yes, this is a lower pH, meaning it is an acid. That's what we're looking at. Common bases are those that can accept hydrogen ions, and it tells us that all of your metal hydroxides, like sodium hydroxide, magnesium hydroxide, any of the metals with OH, can accept a hydrogen ion. Now, before I go any further, let's talk about, okay, why? How can they accept a hydrogen ion? Because don't they look full to you? Don't they look complete? Don't they look happy? Don't they look balanced as far as formulas are concerned? Do they? Okay. This is where we have to pull together what we've learned in this chapter, or this material already. What do things that separate in water, what are they called? Strong electrolytes. Do you remember that?
I have a question about that.
Okay.
Because on the homework, I just don't know when you look at a formula, how you know if it's strong or weak.
Are you on the acids or are you on the electrolytes?
The electrolytes.
If you're on the electrolytes, then if it's an ionic compound, most of the ones you're going to get are going to be strong. Does it say strong and weak? Is there a question about strong and weak?
Like a box.
A box, and you have to pick which one's the strongest and the weakest? And you're sure none of them are acids? Hold on. Okay, hold on and let's go through here, and then if I need to look at it after class, I will. Okay? And it may be something I need to take off, because I'm not going to ask you to discern between strong electrolyte and weak electrolyte on the exam, but I am going to ask you to discern between strong acid and weak acid. So it may be that you can tell based on that. So hold on, okay? Hold on. Now, going back to that, what does a strong electrolyte do when it's dissolved in water? It conducts electricity, but what does a strong electrolyte do? Separates readily when it dissolves in water. These are strong electrolytes. What are they going to do? So what are they going to separate into? Just take this one, for instance. Sodium ion and hydroxide, magnesium and hydroxide. Does that make sense? Which means then you've got magnesium ion floating around and you've got OH -1 floating around. Where's the acceptor portion of that? Who's going to be able to accept an H+? Which one? The Na or the OH? The OH. And what is HOH? Water. So basically what happens is when these dissolve in water, they separate into their ions, which is what allows them then to accept that proton, which is what makes them the base. So when sodium hydroxide dissolves in water, it separates. Then that hydrogen ion can attach to the OH. When magnesium hydroxide dissolves in water, it separates. The hydrogen ion can attach to the OH. Now these two I'll deal with in a minute. Calcium carbonate, is that going to dissociate? Can it? Does it have the potential? Is it an ionic compound? Yes. Now all of it may not dissociate, but some of it will, which means then this is Ca+2 and this is CO3 -2, yes? Does that mean it can accept a hydrogen? We following? Some of you are lost in space. This is your test Wednesday. Pay attention. Be with me. What happens here? Separates. What can we add? Hydrogen. So these, I'm hoping, make sense as to why they are acceptors. I'm hoping that makes sense. The question, though, is, what about this and this? These are molecular compounds. How in the world can they be bases? In fact, really, by definition, could they even be acids? By definition? Yes, why? Do they have hydrogen? They have hydrogen, so they could be an acid by definition. And they also are a base by definition. They're both. How do you know which one they are? It all depends on what they're with. So NH3 as a base, this is what happens. NH3 plus hydrogen ion. Now, if you remember any nomenclature, you'll know who this forms. Say it. Ammonium. NH4 plus 1 charge. So here we have the base, add the hydrogen ion, and so now we have what this became. That's after it has accepted. Water, do you remember what this one would make? Hydronium. Have you seen these two before? Those are the polyatomic ions, the only two that were positive. So the base is without the hydrogen ion. When you add the hydrogen ion, then you get what it becomes. This relationship of what it starts out as and what it becomes is a partner relationship. And those are called conjugates. So if you flip the page, you will see conjugate acid and conjugate base. The word, I have not looked up the word conjugate, but in every view of conjugate that I can think of, it always is basically meaning partner. So let's look at what that would be. The conjugate acid would be the partner to who? The acid or the base? The conjugate acid is actually the partner to the base. It's the partner to the base. The conjugate acid is the partner to the base. It is the product that is formed after the gain of the proton by the base. It is the product that is formed after the gain of the proton by the base. It's on the other side of the equation because it's the product. That's what you have to realize. We're going to be looking at equations. And so the base does what? In the equation, what does the base have the ability to do? Gain hydrogen. So after it has gained the hydrogen, who is it now? The conjugate acid. Does that make sense? So if we went back to that previous page, if I went back to that, and this isn't an entire balanced equation by any means, and it's not balanced at all, but if this is the base, this is the acid in essence because it's the hydrogen being donated. What is this compared to this? If this is the base, who is this? The conjugate acid, meaning it's the partner to this one. If this is the base, what is this? The conjugate acid. And you might want to label that. Let me give you another example. This is in the water after sodium bicarbonate, which is a weak base. It would be a weak electrolyte. It doesn't dissociate readily, but it will dissociate. It forms HCO3 with a -1 charge. What does this have the ability to do? Gain. Now it could be losing, but the way I've set it up, it's obvious it's doing what? Gaining. That means here it is the what? Here it's the base. And it will form the what? H2CO3, which means it is the conjugate acid. So this is the base. After it has added the hydrogen ion, it is the conjugate acid. Yes or no? Is that making sense or not? All right, the conjugate base is the partner to the acid, and it is the product formed by loss of a proton from an acid. It's the partner to the acid, and it is the product formed by loss of a proton from an acid. So if this is my acid, which of those, and I'm not showing what this reacts with, I'm just showing this simply, But if that's the acid and it loses that hydrogen, which of those is the conjugate base? The Cl negative one. Guys, think about it. If it's called base of any kind, what does it have to have the ability to do? Accept a hydrogen. So what happens is, this is the conjugate base. Now, the next few examples here are picture-oriented. I am not the biggest fan of pictures myself for understanding it, but I know many of you love them, so that's why they're on here. Some people have that visual. Some people, I like seeing letters and numbers, but some people need the visual. So with the visual, I'm actually going to add some letters to help me more than anybody else probably. So this is HCl. This is O negative 2. This is Cl negative 1. And this is OH negative 1. Now, what I want you to do first is cover up the right-hand side and the answers. Cover that up if you can with your hand, or just don't look at it for a minute. And the first thing I want you to figure out is, and this one's an easy one, guys, who's the acid? Oh, the only one that has hydrogen, okay? That should not be hard. So automatically, if you know one of these, you automatically know the other one on that side. So if you say HCl is the acid, then automatically O negative 2 is what? The base. So this is the acid, this is the base. Then you look and you say, what does HCl become? Cl negative 1, which means it did what? It lost. So you were already telling me that this was the acid, so that makes sense, it lost the hydrogen. If this is the acid and this is its partner, this is the what? Conjugate base. If this is the base and this is its partner, it's the conjugate acid. If you've had anatomy 2, I'm wasting your time because you probably already know all this. Okay? If this is Cl negative 1, and this is HOH, also called water, this is HCl, and this is OH negative 1. Again, just cover up the answers. We'll just cover up the answers this time. Easy on this one because there's only one choice for who the acid is. Who's the acid in this case? Water. Now let me stop right there for a minute, because that, if I were you, that'd confuse me. Because here's what I would be saying. But water's neutral. And what you're talking about, remember I said there's 2 avenues that we're dealing with here. We're looking at the rule for Bronsted Lowry definition of an acid and a base, and we're going to be talking in a few minutes about pH. When you say water's neutral, what are you referring to? Bronsted Lowry, or are you referring to pH? You're referring to pH. And you're right. You are correct. Water has a neutral pH. Pure 100% water has a neutral pH. But does water have the ability to donate a hydrogen ion? Why? Because it has hydrogen ion. Does water have the ability to accept a hydrogen ion? Yes, because it can become hydronium. So what does that tell us water can do? It can be either. It can be an acid or a base. It can be either. What decides what it's going to do? Have you ever known of a swing hitter? He can swing right-handed or left-handed? What determines what he's going to, how he's going to swing? Which determines usually? True, he's going to stand a certain way, but doesn't it matter who's in the outfield or who's on the bases? Where he wants the ball to go? So he will change his batting position based on where he wants the ball to go and what he wants to happen as a result. That's what water can do. Water can decide, I say that's stupid. Water has no brain. Okay? But depending upon who water is with, water will sometimes lose a proton. Sometimes it can gain. It can do either one. Okay? In this case, water is going to be what? The acid. That means this is the base. If this is the acid, then what does it become? The conjugate base. If this is the base, what does it become? And you got it right. Okay? All right. Let's do the next ones then. Let's do the examples there. This one I'm going to do with you, and then I'm going to let you do these two real quick. A little harder because what do we have a choice of here? They both have hydrogen, don't they? When you have a situation where they both have hydrogen, you have to see what do they become. And that'll answer the question of which one's the donor. So HBr does what? It loses its hydrogen. That means it's the donor, right? Which means, what is HBr? Come on, talk to me. H2O is the base. Now, what does HBr become? The conjugate base. And H3O plus is the conjugate acid. You do the next two. Gavin, are you here? Has everybody seen this tonight? Pass it all the way back to the back too, because I think we have some folks back there that need it. All right, what did you get? Who is the acid? The second one should be pretty easy. Who's the acid? So this is the acid. That means this is the, what's HSO4 negative 1? Conjugate acid, and this is the conjugate base. Yes or no on that? All right, tell me on this one. HCl is what? Acid. What's in H3? And Cl negative 1? And NH4 plus is the conjugate acid. Good. Making sense or not?
Do you mind explaining like the losing and gaining?
Well, if you look at this example, there's only one that has hydrogen. So this is the only one who can be a donor of hydrogen. If you look over here on this side, did it lose its hydrogen? If it lost its hydrogen, that means it donated it. Well, who got it? Right here. So this became the acceptor of the hydrogen. This was the donor. So to start with, this was the base. This was the acid. You don't know that this is the base really until you look at what it became. If you were to reverse this, does it make sense that this is the donor now if you were going in the reverse? See how that's gone? See how this would be the acid if we were going opposite, which is why it's called the conjugate acid. Does that make sense? Okay. Other questions on these? I will be very honest with you. You need to sit and look at this and get this in your brain as soon as we get out of class. Because right now you'll get it, and if you look at it again, you're going to get confused. It can be. But just realize you need to look at both sides. And remember, if you reverse the whole thing, then the words would still make sense. If you looked at it from this side and we're going left, is this the donor because it has hydrogen? So what do we call it? The conjugate acid. Does that make sense? So sit down and look at these. All right, the strong acids and weak acids. This fits exactly like we talked about the strong electrolytes and the weak electrolytes. So if I say we have a strong acid, what we are saying is that it readily donates a proton. or a hydrogen ion. That's what I mean by that. Why does it readily donate a proton? Because it dissociates or let's say ionizes, not dissolves. It dissociates or ionizes in water easily. So as soon as you put a strong acid in water, what is this saying it does? Separates into hydrogen ion and its anion portion. If it does this readily, easily, does that mean a reaction is going to easily be accepting that hydrogen if there's something there to accept it? Which is what makes it a strong acid. It happens easily. That's what makes it strong. It happens easily. The strong acids, there are 5 of them. HCl, HBr, HI, HNO3, and H2SO4. HCl, HBr, HI, HNO3, I didn't write very well there, and H2SO4. These are all the hydroic, right? So what's the name of this one? Hydrochloric, hydrobromic, hydroiodic. Who is this? Nitric acid and sulfuric acid. Your job is to memorize those 5 strong acids. And I'm going to make your life easy. If you'll memorize the strong acids, you don't have to memorize the weak acids, which are what we really want to know about in a few minutes. And I'll show you why. But learn the 5 strong acids. And guys, this is not as hard as you might think it is. Look over here at the periodic table. When we go to the periodic table, what are you seeing over here? Do you see chloride, bromide, and iodide all in the same column? But I know somebody wants to ask, well, why isn't hydrofluoric a strong acid? Now, does anybody have any idea why hydrofluoric would not be a strong acid? No, that's not that well. Let me rephrase that. I'm not a dental person. I'm not going to say it has nothing to do with that, because you may be going somewhere that I'm not there. But based on what we've learned in class, what's special about fluorine? Yes, that's what I want you to realize. Fluorine had the highest electronegativity. Now, what does that mean? When it's with other elements, who hangs on to the electrons that are between them most often? It does. Fluorine does. Now, let's think about definition of a strong acid. You've put hydrogen with fluorine. Who's hanging on to hydrogen's electron? Fluorine is. Is it really wanting to separate? No. Why not? Because it needs everything with it, right? It's going to hang on to it. And so fluorine, because of its high electronegativity, is what keeps it from being a strong acid when you put it with hydrogen. So hydrofluoric acid is a weak acid. But hydrochloric, hydrobromic, hydroiodic are strong acids. That means they readily dissociate. If you look at the periodic table, I didn't make this easy, but it's in a form that you should see is relatively easy. You've got the hydroiodic, hydrobromic, hydrochloric, sulfuric, nitric. Do you see the little path they have here? That is not that hard to memorize, those 5. Oxygen's out of that loop, but other than that, it's a little diagonal and come down. And that's your shape there for the strong acids. And so learn these strong acids. If you learn the strong acids, then you're going to be set for everything else. The weak acids less readily donate a proton. They less readily donate a proton. And in fact, only a small fraction dissociate or ionize. Most remain as molecules, not ions. Does that sound like weak electrolytes? If you've read your notes lately, that should sound very similar to weak electrolytes. It's the same thing, basically. It's the same thing. So they less readily donate a proton, only a small fraction dissociate or ionize, most remain as molecules, not ions. And I'm going to give you the examples here of some weak acids, but guys, don't memorize the weak acids, because what I say, memorize the, and then you know everybody else is weak, so there's not going to be any choice, okay? So acetic acid, acetic acid, carbonic acid, HF, which is hydrofluoric acid, and phosphoric acid. All of those are your, or some of, not all of them, those are some of the weak acids. Those are some of the weak acids. Flip your page and you'll see a repeat of this in a different format. This table is from the McGraw-Hill book, and it gives you the strong acids and their base and the weak acids. Which ones are you going to memorize? You memorize these. That's what you memorize. Because by doing that, if you will memorize the strong acids, then look what you've just basically taught yourself. By memorizing the strong acids, do you now know the weak bases? If it's a strong acid, it has a weak base. So look, iodide is a weak base. Bromide is a weak base. Chloride is a weak base. HSO4 -1 is a weak base. NO3 -1 is a weak base. Now right there, you're probably thinking, how are those even bases? Those are just ions. What's a base by definition? Has the ability to do what? Accept a hydrogen ion. Does this have the ability to accept a hydrogen ion? Yes. All of these do. So strong acids, and you might want to even write this if you're not getting it, these are your weak bases, and it shows you increasing base strength. So these are your strong bases, these are your strong acids, these are your weak acids. Once you know the strong acids, you know the weak bases because they correspond to the strong acids, and you know everybody else that's an acid's weak. Why do I care? Well, good question, right? Well, today, why should you care? Buffers. Buffers are made up of weak acids or weak bases, and that's where we're going with this. There's value to knowing the strong acids. That's what I want you to realize. You're not just memorizing it for memorization's sake. You're memorizing it so you can recognize buffers. Okay, that's why we're doing that. Now, I said earlier there's two avenues that we're looking at here for acids and bases. One is proton donor, proton acceptor, and the other is pH. pH, it's kind of a funny phrase or funny thing really. and it's so simple, we're silly not to know what it stands for. What does pH stand for? Parts of hydrogen. That's it. Parts of hydrogen. That's pH, parts of hydrogen. pH is parts of hydrogen. That's what it stands for. So pH equals parts of hydrogen. And it measures the concentration of hydrogen or hydronium ions in a solution. A little bit of a typo here. My man got too big, and that should be over there. But it's pH measures the concentration of hydrogen ion or hydronium ion in a solution. I haven't said this, but I need to say this. Realize that hydronium ion and hydrogen ion really mean the same thing. Because what does hydrogen ion do when it gets with water? What do you think it does? Makes hydronium ion. So hydrogen ion is the same thing as hydronium ion. They're the same. I could say one or the other. On your test, I may say hydronium ion. I mean hydrogen ion. I might say hydrogen ion. It means hydronium ion. It's the same thing. All right, so the rule is on the pH scale. The pH scale, anybody know what the scale is? 0 to 14. 0 to 6.9 is something, 7 is something, and 7.1 to 14 is something. You just said 7 is neutral. 0 to 6.9 is an acid, and 7.1 to 14 is base. And on the pH scale, what's interesting is as the pH increases, the hydrogen ion concentration decreases. So as pH increases, the hydrogen ion concentration decreases. This is when we have a base. That's what we're dealing with here. If it's a high pH, it's a base. High pH means not much hydrogen ion. Low pH is what? High hydrogen ion concentration, which is where we have more acids. It probably is opposite of what you were thinking. Some teachers have their students do the calculation. It's like the negative log of the concentration and you get the actual number. We're not going to do that. I just want you to know, relatively speaking, who has the higher. So let's say that I tell you that you've got a solution that's 12 molar hydrogen ion concentration, and I tell you I have a solution that's 2 molar hydrogen ion concentration. Which one is more acidic? The one that has the higher concentration or the one that has the lower concentration of hydrogen ion? The higher would, and it will have the lower pH. Does that make sense? Okay? All right, the picture. When I look at this picture, what stands out to me is the blood and the small intestine. Now, why do you think that stands out to me? Compared to the others, why do you think I think those stand out to me? They're both basic. You're right. That's not what stands out to me, but that's a good standout to you. Say it again. You're on the track I'm thinking, I think. I won't use the word exact, but they're steady. There's no range. Do those have one number? There's no range for those. Everybody else has what? A range. So what keeps these steady, exact, the same? I used the word earlier. Say it again. Buffers. Buffers. Buffers keep the pH of blood at 7.4. And the same would be true for the small intestine. In other words, it's buffers that keep it steady, keep it the same, keep it from changing. That's what the buffers do. The other thing that interests me on this chart that I always find kind of humorous and interesting at the same time is, so we put food in our mouth and it starts off anywhere from acidic to basic, slightly basic, not much, but slightly basic. Then it goes where? Which is very acidic, like major acidic. Then it goes into the small intestine, which is basic. Now right there, and I've never had an anatomy class, but right there, my brain says something. I think certain foods are going to, their nutrients be absorbed in the stomach. Am I right? And I think certain foods, the nutrients are going to be absorbed in the intestines. Am I right? I think that it makes a difference that they have a different pH. What do you think? Wouldn't that make sense? Would certain nutrients be broken down, absorbed in an acidic environment, whereas others would be broken down or absorbed in a basic environment? Is that right? I don't know. I'm asking you. You're the anatomy people. Did they say anything about that? No? Yes? I don't remember. You all have had anatomy. I haven't had it. Do they talk about anything like that?
I remember talking about pH, but I only had the first anatomy.
The second anatomy is where they really talk a lot about pH. Are you all doing that yet? You haven't gotten there yet? Okay. 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 Well, that's what my thinking is. I may be wrong, but you can come back and haunt me if I'm wrong. But I think that's what's going on. But anyway, go back to my scenario. So we put in food. It starts out anywhere from acidic to slightly basic, goes to stomach acid, which is super acidic, goes to the small intestine, which is basic, and then ends up in the large intestine before it comes out, and it gets what again? Acidic close to neutral, and I'm really kind of glad of that. Same thing for urine. Why would we be glad of that? Might burn coming out, right? So I'm kind of glad it gets close to neutral on its way out. That would be nice. I appreciate that. Of these things, as far as memorization, I do think you should know stomach acid's acidic. I do think you should know your small intestines are basic, and it starts off and ends up somewhere between, basically. But as far as specific numbers, no, I don't think I'm going to ask you specific numbers other than maybe blood. Now, I may ask you blood, okay? A lot of what we're doing in this section is a lot of putting it together, and it's going to be kind of a big picture thing. Now, on this slide, basically what you're seeing here is something that, again, I kind of went on a tangent with a lot of charts on these. I have several of these pH charts, and it doesn't look like you can see it very well, the colors, but maybe you printed yours in color so you can see it better. There we go. But what you're looking at is several things, honestly, and I'm not going to read these to you. I am showing this to you for a couple reasons. First of all, I want you to sit down and I want you just to kind of pay attention. Drain cleaner, pH of 14. Bleaches and oven cleaner, that's pH of 13. Soapy water. In other words, these are basic. You follow? A lot of cleaning supplies are basic. You go up to the acids, and a lot of your foods and drinks that you're familiar with are acidic. Now, does that mean that all food and drink is acidic? Not at all. In fact, this summer we grew cantaloupe, and I don't know what made me think of it. I always have known that when I eat cantaloupe and then I drink water, my mouth is weird. Somebody's shaking their head. Thank you. I'm not the only one. Okay? When I eat cantaloupe, though, after I eat the cantaloupe and then I drink water, there's just some kind of weird taste or texture or feel or something in my mouth. And I've never known why. But this summer, when we cut the cantaloupe up, it was a particularly slimy cantaloupe, and it was still good. I'm not saying it was bad, but it was very slick. And some reason it hit me, I bet this cantaloupe is basic. And I happen to have pH paper, and I tested it, and it is. Cantaloupes are basic. And it was interesting because I did not know that, but and I'm sure that's why it gives you that feel in your mouth. It's kind of I don't know, for me it does a weird thing in my mouth. And it would be interesting to see if you had other basic foods, if every basic food did that. And I don't know. I can't think of another basic food right now. Or can't think of another food that gives me that same feel.
You know, like the green cantaloupe, it's
Honeydew melon?
whatever that stuff is, my throat's so dry.
Then there could be something going on, and it would be interesting. Does it make a difference if you have an acid with the cantaloupe, you know? And I don't know. I mean, if you drink lemonade with honeydew melon, or, you know, I don't know. But it's kind of interesting that, and I never had thought about doing that before, but it was kind of an interesting thing. The other reason I want you to look at this is, what are these? What do you think this is? Concentration of hydrogen ion. So what is it showing you? It's showing you that very little hydrogen ion has what? A high pH. A lot of hydrogen ion has a low pH. Good. Okay. Well, let me add something here since we've got some room. This is just in general to give you an idea of whether you have an acid or a base. If you want some pH paper, I'll find some for you. But acids tend to be, or let me not say be, tend to feel squeaky clean. Have you ever had lemon juice on your hands or vinegar? And they just feel really like, I can't say the words, it's squeaky clean. That's just what they feel like. They're not slick, they're just very, you can snap good after you put lemon juice on your hands, okay? Does that make sense? So they tend to feel squeaky clean. And you can even put, think vinegar or lemon juice. They strip your fingers of oils. Not that bases also don't strip them, but the interesting thing is that bases tend to feel slick and slimy. And if you've ever had bleach on your hands before, it's like you get the bleach on your hand, you rinse your hand still feels slick because of the bleach. And that's bases will tend to feel slick. So if you ever your hands can kind of give you an indication of what it is. I mentioned, I kind of got on a tangent. Here we go again, some more pH charts. I didn't print mine in color this time. Maybe you did. Why did I do this? I did it because, again, I just find it interesting myself. I think it's just kind of cool to try to figure out what the pH of things are or is. The other reason I did especially this chart is because it actually shows you these, it actually shows you the numbers in a different way. And I wanted you to see those. I wanted you to see the numbers in a different way. And so again, two different ways of looking at it. The moles per liter, that's the molarity. We've talked about molarity before. That's the moles per liter. You can see the very acidic, it's 0.1 mole per liter. When you get up here to the very basic, it's 0.000 and all those zeros in front. Which means, again, this is big or little number. Little number, meaning low concentration. What about the pH? High pH. Higher concentration, and again, that's not high, that's high relative to this, okay? High concentration, what about the pH? Low pH, okay. Let me give you one last question about this to get your brains working a little bit, and I wanted you to have it on your notes. Which has the lower pH? This is my question. Which has the lower pH? And here are my choices, A and B. A is 1.0 times 10 to the negative second molar hydrogen ion. B is 1.5 times 10 to the negative third molar hydrogen ion. What do you think? Don't do the negative log. I'm not asking you to do any of that. I want you to just use your brain. Compare these two numbers. Most of you probably will want to take them out of scientific notation. What is this number? Come on, talk to me loudly. 0.0 1, 2, that means the 1, 0, and this is proper significant figures, not that it matters per se in this example. But that's the molarity of the first one. What's the molarity of this one in decimal notation? 0.0, another 0 or not? Again, 1, 2, 3. That's 2 zeros in front. Guys, now look at them. Which of these numbers is bigger? A is bigger, which means the pH will be lower. So in answer to the question, the answer is A, because this is the higher concentration, therefore lower pH. Higher concentration, lower pH. Making sense or not? All right. Back to reactions again. But this time we aren't looking for conjugate acid, conjugate base. Now we are looking at predicting the products. We are figuring out the products for these reactions. And it tells us what they are going to be. And all I'm asking you to do are two types. Acids reacting with a hydroxide base, acids reacting with bicarbonates or carbonates. The rules are basically the same for these two, so I'm clumping them together, and this one's separate. On your exam, what you are going to see is something, it won't be hand graded, but it's going to be a multiple choice question like this. I am going to give you the reactants, and you have to write the balanced equation. How do you know what the products are going to be? Because you're going to know the rules of what happens. When an acid reacts with a hydroxide base, it tells us it yields what? Water and a salt. Now, you're thinking NaCl, salt. A salt simply means an ionic compound. For our purposes, just call it that. A salt is an ionic compound. It's really an ionic compound that's not an acid and it's not a base, but honestly, if you just call it an ionic compound, you'll get it. And when you write ionic compounds, what always gets written first? Which ion? The metal, if there's a metal in it, or the cation? And these will be metals. There will be metals in these because it's a metal hydroxide, right? So basically what you're going to have every time, and you could do any of these, is you're going to have an acid, you're going to have a metal hydroxide, and what is going to be produced? Go ahead. Water and In this case, who do you think is going to be produced? NaCl. But how do I say right water? Right water is HOH, and I'll show you why. So here's our products. HCl plus NaOH yields HOH plus NaCl. Why do you think I told you to write it that way? What was one of the hints I told you on balancing equations? If it has the same what? Polyatomic ion on both sides? Now what do you get to do? Call it HOH, and there's the OH with the OH. Does that make sense? Okay? So what's going on? 1H, 1H, 1Cl, 1Cl, 1Na, 1Na, 1OH, 1OH. Is it balanced? Yep, it's balanced. We didn't use the term double displacement in here. I didn't tell you the different types of reactions, but this is the key for these. They switch partners. When I teach this double displacement reaction and I talk about all the different types of reactions in the other classes I teach, I call this one, this is like the swingers club. Don't try that, okay? But what do they do here? What are they doing? They're just switching partners. So the H goes with the OH, the Na goes with the NaCl. So if you think of it that way, it's not hard. You shouldn't have any questions about what the products are on this. They just switch partners. Maybe I should say it's the square dancing club, and they switch partners. But what's going on here? On this one, what do you think is going to happen? They switch partners. So what's it going to be? Always it's HOH, and then what's the leftover? Ba and PO4. Now, here's the hard part. You don't know your ions. Because what do you have to do right here? I can't leave it BaPO4. Now, somebody knows their ions, and that's good. But what do you have to know? The charge for Ba and the charge for PO4. So let me give you a trick. If you don't remember the charges, hydrogen's always what? Everything we've been dealing with tonight, hydrogen's been what? +1. Hydroxide is -1. We've seen that over and over and over again. And if you can't remember hydroxide, just remember 1H is with OH. That means it's -1. Even though I know that's not an ionic compound, it still works to say that. That means if this has 3 hydrogens with it, what is PO4's charge? -3. If OH is -1 and there are 2 of them here, this Ba must be what? So use the process of elimination to figure out the charges if you don't remember them. Which means then the formula for this will be what? Ba3 parentheses PO4 2. So we've got several steps here that you have to do. Now balance it. Balance the whole thing. Balance the whole equation. All right, what do you have in front of H3PO4? 2, 3, 6, and nothing, or 1, but you don't write 1. Yes or no? Anybody confused on this? All right, the next type of acid-base reaction you're responsible for is acids reacting with bicarbonate or carbonates. Now, bicarbonate is HCO3 -1, carbonate is CO3 -2. What do those two things right there have in common? CO3. So the key for both of these is look for a CO3. Did these have CO3 up here? No, so we don't even worry about that rule because we know these are the OH, which makes HOH. These have CO3. Every time you have an acid plus bicarbonate, you will get water, carbon dioxide, and salt. Anytime you have acid and a carbonate, you get water, carbon dioxide, and salt. So what are you really looking for? Acid plus carbonate. You just simply look for acid plus CO3. And if you have acid plus CO3, what are your products going to be? So then, tell me what to write here. Now, on these, write it as H2O. It won't help you to write it as HOH here. That will be more confusing probably because then your balancing, you'll get a little more confused on. I would go ahead and put H2O plus what? CO2 plus, who's my salt? NaCl. Let's go ahead and do this one, then we'll balance both of them. Go ahead. H2O plus CO2 plus BaSO4. Now, how do you know it's BaSO4? Because what is Ba's charge? +2. What is sulfate's charge? Say you don't remember sulfate's charge. How many hydrogens is it with? So what's sulfate's charge? -2. So is this balanced? Yes. Now, go through this whole thing and go through this whole thing and balance them. What are you finding out? They're balanced. Both of them are balanced. That's right. They're both balanced. They're both balanced. There are more of these at the end of these notes. I think there's 4 more into the notes. And on those extra practice worksheets, there are, 4 more? So I hope that you will take the opportunity to do the extras. You need to do the extras. You need to take that time to do them. So we've talked about buffers already. Let's really now deal with buffers. If I think of, go ahead, I'm sorry.
Sorry, I just wanted to clarify. So if every single time, I don't know if it was like a pattern or like this topic is now, but every single time, if we don't have to add subscripts, so the coefficients always all be 1. So like if we don't have to
And if the charges are all the same.
yeah.
Like up here, it was +1, -1, +1, -1. Yes.
So you won't ever have to use those.
No. I mean, I still would check it just to make sure you haven't messed something up, but yes. Yeah. That definitely is there's a reason behind that. Yep. Good. Good observation. All right, buffers. Give me a synonym for the word buffer. It may not be a dictionary synonym. Just give me something you think of when you say buffer. Keep going. Think of buffers in this world besides pH buffers. A buffer is a Say it again. I can't follow you. Say it one more time.
Like a start?
A start?
Yeah.
No. Let me tell you what's a buffer in your car, the bumper. Now, your cars today are built a little differently, but airbags are buffers. Say it. Helper. So what'd you say?
Like lessens the blow.
Lessens the blow. I can't talk. Resists change. Protector. Lessens the blow. Now, what does a buffer with pH do? Lessens the change, protects the pH, resists change, and it's a helper. It is. All those things that you've said. All of those. And that's what it tells us. A pair of helpers that resist pH change. But the key here is it's a pair. It takes two things to be a buffer. You have to have two things to make a buffer. So here's what makes the buffer. Buffers are made up of weak acid and its conjugate base or its salt. Buffers can also be a weak base and its conjugate acid or its salt. So the pair is the weak acid and its base, or the weak base and its acid. That's the pair. Why did I tell you to memorize the strong acids? Why did I tell you to memorize the strong acids? So you know the weak bases, because those are their conjugates, and if I already said, if it's not a strong acid, it's a... So really, by telling you to memorize the strong acids, even though we really aren't that interested in them, that was only 5 things to memorize. That lessens the amount you had to memorize. So just learn the strong acids. Everybody else is a weak acid, or if it's the base of the strong acid, that means it's a weak base. Then you look and say who's with it, and if it's the salt of that acid or base, then that will be a buffer, potentially a buffer. It can make a buffer. Buffers are huge in our body. We have the blood buffer is this H2CO3, HCO3 negative 1 buffer. That's the principal buffer in the blood. Guys, we have dealt with this earlier when we talked about hyperventilation. What were we talking about? What was in the blood that I didn't know about? Carbon dioxide, right? I mean, I won't even go into that discussion again. Bottom line, I've learned it. Okay, CO2 is in our blood all the time. I know that. Oxygen is in our blood all the time. But what does CO2 and water make? Add them together. H2O plus CO2. Hydrogen carbonate, which is H2CO3, which is what? What is H2CO3 when it's in water? Carbonic acid. Do you realize that? So when you can make carbonic acid. You remember blowing bubbles in your drink and your mom fussing at you with your straw? You know what I'm talking about? You were making carbonic acid. You were making carbonic acid in your drink. When you blow out carbon dioxide. When it mixes with the water, you're making carbonic acid. Carbonic acid is in your blood. Why? Because what's your blood made up of? It's got carbon dioxide in it and it's got water. Is there going to be some carbonic acid there? Is there going to be some bicarbonate ion there? Yes. That's the principal buffer in the blood, which keeps the blood at what? 7.4. This is what maintains the pH at 7.4. That's the buffer that does that. That's the buffer that maintains the pH at 7.4. Now, scratch through this. I'm not going to worry about this tonight. Come down here and tell me which of these are buffers. First, what do you do to figure out if they're buffers or not? They're buffers if they are what? A weak acid or a weak base. So here's the first thing to do. Look through there and see if there's any strong acids. Is this a strong acid? Yes, it is. It's not a buffer. You don't have to look any farther. It's not a buffer. H2SO4 is a strong acid. So can it be a buffer? No. Strong acid? Nope. So both of these are strong acids. Now, I'm going to slow down a minute because I lost some of you there. Let me come back to this one. Yes, that's how I want you to do it. I want you to know those strong acids, so immediately you see a strong acid, you don't give it a second look, but I'll give it a second look right now. The second look is, what about its partner here? What else is here? Put your phone up, hon. Put it up. If this is a strong acid, is this even the conjugate or the salt of that? Are these even partners? No. They look a little similar, but what's really different? O. Does O have anything to do with conjugates? No. So that's not even a real partner. Now look at these. I agree, this is a strong acid. But is this the salt of that strong acid? Yes, it is. If this were a weak acid, would this make up a buffer? Yes, but it's not. It's a strong acid, so it's not a buffer. Now, what about this one? Is this a weak acid? Is this the salt of that weak acid? So is this a buffer? Yes. This is a buffer. And why is it a buffer? Because this is a weak acid. Yes or no? And this is the salt of that weak acid. This is the salt, but it's not a weak acid. That's what keeps that one from being. Buffers are pretty amazing. And like I said, they're protectors. This picture shows us that. I'm not going to go through this a lot. You've got the description of what's going on here at the bottom. But it's showing you real quickly the pH of water. Here we've got 7. You added a little bit of hydrochloric acid and immediately what happened? Dropped it majorly. Same water, pure water, add a little bit of a strong base. What immediately happened? Raised it tremendously. So is that system protected? Is that a protected system? No. Did we have swings? Did we have swings? Yes. Yes. Here, it starts off at 4.74. Now, different buffers have different pHs. This pH just happens to be 4.74. You add a little bit of the hydrochloric acid, what happened to the pH? Not much. You add a little bit of base to that, what happened? Not much. So tell me about it. Is it protecting? Is the buffer a protector? The buffer's a protector. That's what we're looking at. That's what a buffer does. Pretty amazing. Now, I mentioned this last week, I believe, when I started teaching this class and I asked people that were nurses what you needed to know. I kept hearing these terms, so we're going to talk about these. Metabolic acidosis, metabolic alkalosis, and then the respiratory equivalents. What are they? Well, metabolic acidosis is fallen blood pH. Fallen blood pH, meaning lower than normal. It can happen in poorly controlled diabetes, or severe infections. It results when excessive amounts of acid is produced and blood pH is lowered. I have a theory, and I have the people to answer it in this class. My 8 o'clock class didn't have this. All right, my theory is, or let me go backwards, part of it's not my theory. Part of it's what I've read and what I've heard. Bacteria in your mouth. This is for my hygiene people down here. Bacteria in the mouth causes extra acid in your mouth. They're shaking their heads yes. Which contributes to tooth decay and cavities because it breaks down the enamel on your teeth. Okay? And sugar actually causes more bacteria because it's like feeds the bacteria, which is why tomorrow night after you eat all your candy, brush your teeth before you go to bed. Okay? Huh? And every other night, she says. Okay? So there's your dental hygiene plug for the year. By the way, this is a plug for them. They don't know I'm doing this. I don't know if you all can do it, but I think you can. They are selling Oral-B toothbrushes. Can they do that too? Can the students buy those too? They are so cheap compared to what you would pay for them. They're the brand new Oral-B Spin Doctor or Spin Master or whatever they're called. Whatever, Spin Genius. I have one. Not from them, but I have one from another dental hygiene student actually. But they're selling those cheap. If you want to like get yourself a Christmas present or just get yourself a good toothbrush, you should see one of them. Okay, they're taking orders now. They're not paying me to plug that. 65? Is that right?
I think it's mainly the second years that do that, but we know that they're selling.
Well, no, compared to buying it on the shelf at Walmart.
Yeah, they're way cheaper.
Yeah, way cheaper compared to buying it on the. Yeah, they're like double that if you were to go. But see, the benefit is you just use the. You don't have to change the whole toothbrush every 3 months. You just change the head. I'm telling you, it comes with 3 heads. It comes with 3 heads. That's a deal now. I'm telling you, it's a deal. I'm telling you, this is a deal. Anyway, I got to get off topic there. But anyway, so let me go back to my theory on pH and metabolic acidosis. So if, this is my theory, and you guys tell me now, they are confirming that what I said was right in the sense that bacteria causes acid, da-da-da-da. If bacteria causes acid in the mouth, then would bacteria cause acid in the whole body? You are the anatomy people, is that right? You've had micro, is that right? So if you have a severe infection, is that going to affect not just your sore throat, but can it also affect your pH of your blood? Anybody think yes? I think yes. Okay? I just found that interesting. I just kind of discovered this in my head today. I was kind of, like thinking. All right, metabolic alkalosis. pH rises due to decreasing amount of stomach acid. pH rises due to decreasing amount of stomach acid. What can cause a decrease in the amount of stomach acid? Say it. Vomit. You got it. Excessive upchuck, right? I think I'm going to put that. I never know if I spell vomit with 2 T's or 1, so I'm just going to vomiting. I don't know if vomiting is with 2 T's or 1, so I'm going to say excessive upchucking. Excessive upchucking, you can call it what you want, can cause decrease in stomach acid. let's go back to those teeth again, and let's go back to those folks that like to throw up. Don't do that. What happens if you make yourself throw up? Not only, that's called bulimia, by the way, not only does that, sure, you get the food out of your stomach, but you get the acid on your teeth, which again goes back to tooth decay. And then not only does it get the acid on your teeth, but what else does it do? It tears up your throat. Oh, I forgot about that one. It just totally tears up your, I mean, you're just think of 1.6 pH all up and down there. And then you're also decreasing the amount of stomach acid, so you could end up with metabolic alkalosis. It's just not worth it. So please, if you know, seriously, if you know of anybody who does that, man, try to make them really realize how bad it is. Okay? Respiratory acidosis and respiratory alkalosis. You've got some pictures here. I'm not going to show you the pictures. You can read the pictures on your own. But here's the deal. Respiratory acidosis results when the body retains too much CO2. Now, if you read the picture, you'll see that thing I just talked about, CO2 plus H2O makes carbonic acid, which is what's going on here. So if you have too much CO2 in your body due to not breathing it out, then what can you have? Respiratory acidosis. Respiratory alkalosis can be caused by hyperventilation. And this is the one we talked about earlier with the blood pressure scenario. It can be caused by hyperventilation. Breathing in this manner eliminates too much CO2. And if you get rid of too much CO2, then what do you have? Less what? If you get rid of too much CO2, you have less carbonic acid, right? Which is part of that buffer, which keeps the pH at 7.4, remember? It all works together. So if you breathe in this manner, it eliminates too much CO2, causing a rise in pH due to not enough H2CO3. And again, take the time to read the pictures because it gives you definitely more details. All righty, back to the calculator now, and that's what we're going to finish up with. Going to finish up with math. So on this page, I really love this section. It's I don't know, you probably don't because you're probably overwhelmed, but all of this, if you will sit down tonight and read through all of your notes from the first to the end for this test, I think you will start to see how it fits together. And it fits with what we've done before. When we did moles, stoichiometry, etc., all this is just coming together. It's putting it together here. These top two problems I'm not going to do tonight. I'm not going to do with you. You can do those later. Really, it's on here as a review of what's going to be dealt with here, and so I'm going to do it again here. But just refresh your memory real quickly. Tell me, what would you do on these two problems? Thank you. That's what I wanted to hear. Change the ILM to mole per liter. Change the ILM to mole per liter. And then do you immediately have the setup for dimensional analysis problems? So I shouldn't have to do that. That is like old school. You know what to do there. So skip those. Now, what do you see here? And numbers. As soon as you see balanced equation and numbers, what word should come to your mind? Stoichiometry. And when you start to look at these numbers, at first you may get kind of flipped out because it's like, oh, wow, but there's two numbers. But guys, what were these? So what is that going to be? A conversion factor. Why do I need that? Because I need to get into what? Moles. Why do I need to get into moles? Mole to mole ratio. Let's do it. Let's do it. What's going to be your given in this problem then? 500 milliliters. I love that. You guys know it. That's awesome. And it's 500 milliliters of who? BaOH2. What do you do now? How? What's going to be on the bottom? 10 to the third milliliters. What goes on top? 1 liter. Milliliters cancel. Is it still BaOH2? Okay. Now what? What goes on top? 5.75 moles of who? BaOH2. What goes on bottom? 1 liter. Liters cancel. Boom. What are we ready for? Mole to mole ratio. So you go up here. You're looking for AlOH3. What goes on top? No, pay attention to who you have. Who goes on top? The AlOH3, so what number? So it's 2 moles of AlOH3. What goes on bottom? 3 moles of BaOH2. Moles of BaOH2 cancel, and that's what you needed was moles of AlOH3. Run your numbers. Isn't that awesome that you guys understand dimensional analysis that well, that you did that so easily? What's your answer with proper significant figures? 1.92 moles of AlOH3. Yes or no? All right, the next one. Similar, but a little different. This time we are reacting, in this problem, we were reacting a solution with something, and it probably was another solution. It doesn't tell us, and we got a solution. That's how all this worked. In this one, though, we have a solid, and it's reacting with, I'm sorry, we have a solid that's produced. I said that wrong. We have a solid that's produced, and it's reacting with 2 solutions. One of the solutions is sodium sulfate, and I give you the molarity. What you don't know is what? How much volume does it take to produce this? So we start here. And if I give you the molar mass, you use it. Don't go calculate it on your own. So 0.668 grams of barium sulfate. What do we put on bottom now? 233.40 grams per 1 mole, and that's still BaSO4. Mole to mole ratio. What goes on top? 1 mole of who? Na2SO4. Good. What goes on bottom? 1 mole of BaSO4. Now, what's my next step? What is the conversion factor? The molarity. Right there it is, the molarity. The molarity. So what goes on top now? The 1 liter. What goes on bottom? 0.113 moles, and that is the Na2SO4, and then simply liters to milliliters. Now some of you are just simply, you're like just copying what I write. I hope you're thinking, because if you're just copying what I write, it's probably, you're not going to know what you're doing when you do it later. So try to focus and be engaged and think while you're doing this. What's your answer? 25.3 milliliters. And I'm going to leave off the units for right now. It is sodium sulfate. What's missing in this next problem? There's no balanced equation. Now, why did I do that to you? What's part of your test? Neutralization reactions with metal hydroxides and acids. So, let's do it real quick. What's the acid here? It doesn't matter which one goes first, but we'll do the base first. It doesn't matter. NaOH plus H2SO4 yields. What's the rule for an acid reacting with a metal base? Water, how do I write it? HOH, and it's going to be NaSO4. But now what's wrong with just leaving that as NaSO4? It's not balanced formula. What's sodium's charge? +1. What's sulfate? -2. So what do I have to do here? 2. It's Na2SO4. Now, do we have to balance it? So balance it. What do I do to balance it? What goes here? 2. Okay. I won't do that to you on the test. Why did I do it here? Because that's part of your test. But on your test, if it's a stoichiometry problem, I'll just give you the balanced equation, then you do the stoichiometry problem. But since we're studying for a test, that's part of what we're doing here. All right, what makes this problem the hardest of these 3 is that you have 3 numbers now, and you're not quite sure where to start. Figure out what you have enough information of to get you into moles so that then you can do the mole-to-mole ratio. Which substance do you have enough information about to do that? Which substance? H2SO4. This substance you have enough information about to get you into moles. The other way you could have determined that this is what you're going to start with is because this is a conversion factor, so that can't be it. That can't be it. That must mean this is it. So there's 2 ways of looking at it. 5 milliliters of H2SO4. Same thing we've done on the top problem. What do? Convert to liters. Then what? What do we put in here now? 6.0 moles of H2SO4 over 1 liter. Mole to mole ratio, good. Do it. Keep going. Follow or not, guys? Now what's interesting is do not pick that calculator up. Put the calculator down. Look at what you can do. Look at what you can do. 1,000 cancels. What else? 2's cancel. What's the answer? Thank you. Yes or no? All right, I want to show you something. This is the bottom problem we just did. This is the second problem on the next page. Guys, it's the same thing basically. See previous. You're going to do that one on your own. Now, this problem is the hardest of any problem we've done. And I want us to do it together and then we'll stop. This is an acid-base neutralization reaction. Acetic acid HC2H3O2 plus who? NaOH. What's that going to make? HOH and sodium acetate. And it is balanced because everything's +1, -1. So that's your balanced equation. Read the question and tell me what you think you're going to start with. $15.5 milliliters is what you start with. Why? Because you give enough information from that, or you get enough information from that to get what? Moles. Now guys, before you start going, think for something else here. Before you keep going, I'm going to stop for a minute because some of you are just watching me do it and you're just copying it down. You're not thinking. I want you to think. If this is going to be your given, this information will give you what? Moles of who? NaOH. What are you trying to find? Molarity of who? Acetic acid. So in order to find the molarity of anything, what do you have to know? Moles and liters. Do you have information to get you liters? Yes. What do you not have? Moles. So the stoichiometry part of this problem is simply to get you from here, using this to get moles of NaOH, and then mole to mole ratio to get moles of acetic acid, then that answer is going to be used in a molarity equation. So this is a two-step process. So let's do the stoichiometry first. Do this, get to the mole to mole ratio. All right, are we here? What's my next step? What goes on top? 1 mole of who? And what goes on bottom? 1 mole of NaOH. And then I stop with stoichiometry. And you get on your calculator, I believe, 0.0031 moles. Do you get that? And then I know that molarity is mole per liter. I now know the moles. What do I not know yet? So how do I get that? Well, I know that my 25 milliliters can be converted to liters. And a lot of you can just do that in your head, and I'm fine with that. And I'm drawing a lot of arrows, but I'm doing this because if someone's not here or they're not really following, they can see where that came from. So this is your volume of acetic acid. What's the moles? It's what you just got. So what's happening? 0.0031 moles over 0.0250 liters, and what do we get for our answer? 0.12 molar. Could you also write it as 0.12 mole per liter? Sure. Sure. Yes or no? Now, I want you to stop. Quit putting your stuff up. Guys, give me my 7 minutes. Get your 7 minutes worth of paid tuition, okay? Chill for a minute. I want everybody to sit and look at that problem. And I want you to make notes to yourself. I want you to think about it. I want you to talk it out inside your head or outside your head. And make notes on what you just did. Because some of you are about to go off into cell phone world and you're going to forget. Pay attention right now and I'm going to be quiet for 30 seconds. Are there any questions on that problem? Or the other 3 that we did that were similar to that one? I mean, they were similar but different. Are there any questions on solution stoichiometry? Okay, at the bottom of this, I told you that you would have some more practice problems for balancing equations. Here are some more problems. This is what your test will include. You're going to see this on there, okay? I'm going to write something that'll help you down here. This is just like when I did the nomenclature, I called them kind of like quick notes. This is going to be like a quick note for equations here. There are two basic types of acid-base reaction equations I've told you need to know, and this is it. Acid plus something OH yields salt plus HOH. Does that make sense to you when I write it like that? So if you find an acid and you've got something with OH, you're always going to get out HOH and a salt. When you have an acid plus something, CO3, you're always going to get out what? CO2 plus H2O plus salt. That should help tremendously when you're doing these. And then the next page as well. You have on Blackboard 2 pages of extra practice problems, which include not everything that's on this test. I don't want you to think this is all that's on the test, okay? What I've put on this practice for you are some of the things that require more doing rather than thinking, okay? The biggest difference in this exam and the previous exams is what I emailed about and what's the announcement on Blackboard. This test has a matching section. None of my other tests have had a matching section. The matching section it's an unusual way to do match, or maybe not unusual, I don't know. I'd never done it before until these tests. But here's the setup, and it's explained on Blackboard, but I'm going to try to explain it to you here too. There are 15 questions. It's like multiple choice, but every response, A, B, C, D, E, has a right answer corresponding to it. Nothing's used more than once, and nothing is not used. Everything is used. So here's the setup. You'll have 5 phrases or terms on the left. You'll have 5 on the right that go with these 5. Skip a couple spaces, you have 5 more that go together. Skip a few more spaces, you have 5 more that go together. Now, none of these sets go with the other set. It's these 5 go together, these 5, these 5. Okay? Here's what makes it hard. If you get in a hurry and you run through it and you really don't read, it's going to cause you trouble. Overall, it's not hard though. Let me explain why I say it can cause you trouble. Here's how I might word something. I may have, for instance, over here on the left, I might put Bronsted Lowry acid, and I might put strong electrolyte. Over here on this side, I might put HCl as one of the choices. Now, if you saw just that, could HCl be the answer for both of those? HCl is a strong acid. Is it also going to be a strong electrolyte? Yes. Is it a Bronsted Lowry acid? Yes. So how do you know which one it is? Here's what you do. You're going to put, I don't know, for yourself. You're going to make that note, and then you're going to keep reading this side. What if you also see something down there, for instance, hydrogen ion donor? What would hydrogen ion donor go with over here? If it were just those 2 and 2. Bronsted Lowry acid, what would HCl go with? Strong electrolyte. Now, what instead of, let's say if instead of putting on there hydrogen donor, what if I put NaCl and HCl? And I still had these over here. Then how would you do it? NaCl would go with strong electrolyte. HCl would go with Bronsted Lowry acid. You follow? You've got to pay attention, okay? I strongly encourage you, like I said, tonight, work on this, okay? Do not wait. Do not wait. Work on it tonight, okay? Try not even looking at your phone until you look at your notes. What a novel approach, okay? It is matching. It is matching.